Okay, so let's talk about nested sigmas. Nested sigma just means that you have one sigma inside another. So we say this one is nested inside the other one. So how do you evaluate an expression like this? Well, pretty much like you do in basic algebra. You evaluate what's in the parentheses and work your way outward. In this particular case, we need to think about what sum j equals 2, 0 to 2 of 1 is. Well, there's 3 terms here, so the sum of these 3 terms is going to be 3. So we can simply replace this sum here with the 3 and get our result, because the remaining sum has 4 terms, which we add to get 12. All right, so the sum of the sum, the inner sum, turned out to be 3. There are 4 terms in the outer sum. When we sum those 4 terms, it turned out to be 12. Now, that was a very simple case. It's quite possible to have cases where the inner sigma depends on the index variable of the outer sigma. In this case, it's a little more complicated. Well, let's see what we get here if we try this. Suppose we consider the sums here. Now notice we have I equals 0, I equals 1, I equals 2, I equals 3. So we're actually going to have 3 terms, I equals 0, I equals 1, I equals 2, I equals 3. So I'm going to list these out, and then I need to evaluate this inner sum for these 4 different values. Now, when I equals 0, I have sum from j equals 0 to 0 of 1. And don't think that's 0. There's 1 term in the sum, because j equals 0 is the smallest value, j is 0 is the largest value. That's 1 term. Now, when j equals 0, the term inside is still 1. So the value here is 1. Right now, when I equals 1, we have j equals 0 to 1. So that's 2 terms. Each term is a 1. So I'm going to get a 2 here. Next term, we have I equals 2. And you can work that out. There are 3 terms here. I equals 3, you have 4 terms here. So we need to take this sum. Now, you could just do this by hand. Just to remind you, I could also write this inner sum. I could write this total sum as the sum from I equals 0 to 3. Now, what is this term in each case? When I equals 0, it's 1. When I equals 1, it's 2. When I equals 2, it's 3. When I equals 3, it's 4. You can see that what's inside this sum is I plus 1. Right? Just look at the pattern and see the number is 1 plus the index. Now, you can write that as the sum from I equals 0 to 3 of I plus the sum from I equals 0 to 3 of 1. That's one way to do it. Now, sum I equals 0 to 3 of I is the same as I is 1 to 3 of I, so that's just going to be 6. And then this one, I equals 0 to 3 of 1, that's 4 terms. This is going to be 4. We get 6 plus 4 equals 10, and that agrees with this value here. There are a number of different ways to break your sum up. I'm just showing you, reminding you of some techniques. Okay. Now, the index of the outer sum can appear anywhere in the inner sum. It could appear at the lower limit, it could appear in the summand, or it could appear in some combination of lower limit, upper limit, and summand. Okay? So be aware of that. Now, when using nested sums, you can switch the order of summation. If you remember, when you integrated, you could switch the order of integration. But you have to be careful about the limits. Same in integration. If the inner integral limits depended on the outer integral, you had to figure out what the new limits were. Very similar with summation, nested summations. All right, so how can we change the 2 summations here and adjust the limits accordingly? Well, let's look for all the pairs I and j that are involved in this sum. What you're doing is you're summing over this expression for all different values of I and j. And if you think about it, when I is 0, it goes through here. When I is 0, j must be 0. When I is 1, j is 0 or 1. When I is 2, j is 0, 1, or 2. So we get these combinations. And let's see. And we can plot these on a graph and see what we got. All right, these are the points that we have in our sum. Now, if you think about the way this sum works, here you're fixing I and you're summing j. So you're actually summing this way. You may remember in integration, you would sum, when you're integrating over areas, you integrate over the area one way, or you could integrate the other way. In this case, we're integrating, we're summing in vertical columns. Okay. Now, that's the way that we sum when we do this. Now, it's quite possible to sum in horizontals. So let's see what happens when we do that. If we sum in horizontals, we'll sum this, and this, and this. Okay. Now, in this case, we're taking j equals 0 as our first sum, j equals 1 is our second sum, j equals 2 is our third sum. So our sum is actually j equals 0 to 2. All right? Now, for each value of j, you're summing over I. Okay. Now, what's the smallest value of I in the sum? Well, in the first sum, the smallest value is 0. That's when j equals 0. In the second sum, the smallest value of I is 1. That's when j equals 1. And the third sum, the smallest value of I is 2. That's when j equals 2. Okay, so we can see actually the lower limit for the I sum is always equal to j. Another way of seeing that is here you have the line here. This 45-degree line corresponds to I equals j, and you're starting your sum on that line. So you're starting your sum across when I equals j. Now, what's the upper limit of j? Well, here was 0 to 2, here was 1 to 2, here was 2 to 2. It should be pretty clear that the pattern says the upper limit is always going to be 2. Right? And then we're summing, in this case, our summand is 1, so we keep the same summand. Okay, so that's our new sum, and that should agree with what I have down here. Okay. All right, so here's some more practice. These ones are a little more complicated, but you can draw the picture and see what's going on with all these cases. If you draw the picture, you'll see how to do it. Here you only need to rewrite the sum. Now in this case, if you have a nested sum, the outer summation index can be treated as a constant in the inner summation. Okay, so let's follow this through. Suppose I have the sum I equals 1 to 9 of the sum of j equals 1 to 7 of ij. I didn't draw the parenthesis, that's understood. Now in this inner sum, I does not vary. What does that mean? I can pull I out of the summation in front of the summation, just as I could if I were a constant. Okay? The resulting sum here, I emphasize by putting parentheses here. No, in this case, this summation is a constant with respect to I. As I changes, this summation doesn't change. So I can pull this summation out of this summation, and I actually get the product of two summations. If you sum I equals 1 to 9 of I, you get 40. Sum this one, you'll get 28, and that's your result. Now you can use various techniques to evaluate some of these sums. Have fun with that. Now, one thing you can notice is that if you can break sums up in this, you break this sum up into two sums. There are various things you can do. You can exchange the integral limits. You can break the sums up. You can change the variable if you like. You can do all of those things. And we'll stop there.